Hey, hello there. Welcome to this session on SystemVerilog Data Types. So in this session, we will look at the different data types that are supported in the SystemVerilog. We will start off with what's there in Verilog and how SystemVerilog builds on it, and then we'll look at like if you assign one data type to another data type, then what are some of the rules that needs to be followed and what happens. So we will understand those details in this session. Okay, this is the agenda for the session. So we will briefly look at the Verilog net versus variable. We have used it in our earlier projects, but we will look little deeper into it. And then the same concepts in SystemVerilog, the terminologies that are used, we will familiarize ourselves. For the net versus variable, the terminologies used in SystemVerilog are slightly different, so we will familiarize. And after we do that, then we will look at the different variable types. So the variable types supported in SystemVerilog are much more than what we had in the Verilog. So we will look at them. Look at the different integer data types, real data types. Then we have class. Class itself is again a user defined data type. Then we have a string data types. Then there's a event data type that user defined named events can be created. And then we have user defined types, which can be enums that can be created. So we will look at all of them, and then we will briefly look at the second part where we will look at like the type compatibility, that when you assign one type to another type, how do you go about it, and then what are some of the rules. And then we will look at like static casting and dynamic casting, what is the difference, and which one to use when. So that is the agenda for this overall session. Okay, we'll start off with the Verilog data types, and the Verilog has the overall data types in Verilog are divided into two categories, the nets and variables. And then before we go slightly deeper into each one of them, one of the things that I want you guys to understand and remember is this concept, we deal with it very closely when we connect the DUT to the test bench. And when we do that, any input ports of DUT, you need to drive it with the help of variables, because those variables will be driven by the test bench. So that's the rule that you need to follow. And then any output port from the DUT, you connect it with a wire, and that wire you pass it on to the test bench for reading. And many cases we do not have like multiply driven wires. So in those cases, you can also use a logic data type, which is a new data type that is introduced in the SystemVerilog. And then any in-out type of a ports that you have, then that you need to model it with using the wire itself, because there will be multiple drivers that will come into play, and you need to use the tri-state modeling to manage the multiple drivers. So I'm just showing one example over here. So we have the direction which decides whether the port is being driven or being read, that is whether it is acting as output or input, and then the output value that we want to send out, and this is the actual wire that we are driving in a in-out mode. And the way you do it is that we say if the direction is drive, then you send out the value that you want to drive as an output, otherwise you drive the high impedance value, and then you read the bidirectional port from whatever the value that is driven from the other side. So whenever some value is driven from the other side, and this we are driving high impedance, it resolves to the value that is driven, so that way you get to know what is driven. So this is the one of the rules that you need to remember, that how a DUT gets connected to test bench and what data types are used. Okay, the net data type, it represents the actual physical connection between gates or modules. You can think of it like a simple plain wire. And as you know, if I have just a wire, it doesn't store any value. Okay, and its value is derived only when it has a driver. Like for example, on your breadboard, you might have a wire that is connecting to LED. Just because you connect a wire to LED, the LED won't light up, right? You need a power source, and only when you connect that wire between LED and a power source, when it has a driver as a power source, is only when the LED is going to light up. And it's a very common form of net data type. What do I mean by this is that there are different forms of net data type. The wire is not the only one. That is one that we frequently use, but there are other data types that we don't use every day, but it is used in case of some special modeling of cells and primitives. In the backend library development, the VLSI library development, those other data types are used. Like some of the examples are, you have like a tri-state net type or a wired, and there is a supply type of a net data type that are available that in the Verilog as well, that can be utilized for modeling. Okay, whenever it comes to wire, the first key concept that we understood was that it doesn't have any storage. So because of that, the wire has to be always, the LHS of your continuous assignment statements, that it needs continuously, it needs to be driven. So that is the one key point about the wire. And that's why it can be either LHS of your continuous assignment statement, or it can be an output port. The second key point that we need to understand when it comes to wire is that it can take these four states, that is 0, 1, Z and X. 0 and 1 are anyway the normal values, and the significance of the Z and X comes from the fact that a wire can take multiple drivers. This is a very important point. A variable cannot take multiple drivers, but a wire can take multiple drivers, and having multiple drivers on a wire is not a error. In fact, it's a feature of the wire. And what happens is, now the question is, when multiple drivers drive the same wire, what happens? That is the question that comes into play. And that answer to that is, there is a concept called resolution function. So whenever a wire is driven from multiple drivers, the value that the driver is driving along with the strength with which, so this is a concept of strength that comes in, whether it is weak, whether it is strong, whether it is supply. So there are different strength values that are defined. So with what strength value and what is the actual value, whether it is 0, 1 or whether it is driving high impedance. So what is the value that is being driven by the driver? This is passed to a built-in resolution function. So the resolution function is built in, so you can that values get passed, and then using that resolution function, the resolution function table is like a truth table, that if these are the two values, then what is the output value. So it resolves to a particular output values, and that is what you will end up seeing on the wire. So that is how the wire data type works. Okay, so we have already looked at the net data type. The second is the variable data type, and this is the data type that is what we are used to in the common procedural programming languages as well. And this, in the context of Verilog, if you are doing a design, then it's used for modeling the storage. And note that just because you declare a particular variable as reg, it doesn't become a storage. It needs additional modeling. That is, you need to have some sort of an event or a trigger, and on that trigger you are assigning the value is essential to for the synthesis engine to interpret it as a register, right? Otherwise it won't become a storage by itself. And what happens is, compared to wire, once the value is assigned to the variable data type, it holds the value till the next assignment takes place, right? And then is also one of the reg is also very common data type used. And note that although we commonly use it for modeling the storage, it is not necessarily true that it has to be always used for the modeling of storage. It is a best known practice, but from the point of view of the possibilities, you can use the reg for modeling the combinational logic as well. There's nothing that really prevents, because all that the synthesis engine cares is that if on all value changes, if a particular LHS is assigned all the time, that means it's a combinational logic. So that's why I'm saying it's always star. When you use always star, what happens is, whatever the variables that are you have using it on the right hand side of any assignment statements that you have, they will all come as a part of sensitivity list, and as and when any value changes, it's going to go through the evaluation and assign some value to the RHS. And hence you can use reg also to model the combinational logic. Not recommended, but you can do it for the heck of it. And then there are other variable data types, like you have integer, you have time, you have real time. So these are other data types, like variable data types that are supported in the Verilog. And just to summarize, net versus variable, any combinational logic, you use the wire, and then you can also use the reg for modeling with always star, as we talked about, and then you can use wire for modeling the shared bus driven by multiple drivers. And this is the like the truth table that I was talking about, and you will be able to see such truth tables for different net data types. Okay, so and then it will show that if 0 and 0 is driven, then what will be the output. If 1 and 1 is driven, then what will be the output. So this way you will be able to see the truth table for the different types of net data types. And then for the sequential logic storage, you use the reg and you can use them in the always block, having a clock as a trigger. Then the value can be assigned to reg on the trigger, and when you do that, it infers the storage. Okay, so in the Verilog, as we saw, the most of our data types were 4-state data types, that they could take value 0, 1, x, and z. Now SystemVerilog has introduced some of the data types that can take only 2 states, that is logic 0 and 1. What happens is, if you remember our Testbench layer, at interface layer level, we could potentially have 0, 1, x, and z's, but the components above the interface layer, where you are either doing transformation from one transaction type to another transaction type, or you are doing the stimulus generation, then you don't really deal with x and z's. Okay, so in those cases, instead of using 4-state data type, you can use a 2-state data type, and just because the fact that you're never going to use these values. And second thing is that it also helps you optimize in terms of storage. And so you can for any of the test bench modeling, you can definitely use, for the higher layers, you can use the 2-state data types instead of 4-state data types. And then there are few more terms. The overall net or variables that we saw in case of Verilog, they are called as signal kinds. And then the definition for data type is set of values and set of operation on those values. Like for example, logic can take 0, 1, x, and z. The integer can take like either a signed or negative, signed or unsigned whole numbers, and like arithmetic operations are allowed. So set of, like, we will see some of those, like what are the set of values that are allowed on each, that the set of values and the operations in fact define the data type. And data types can be used to declare the data objects or define user defined data types. So there is a concept called typedef, wherein you can create sub data types, or you can alias an existing data type. So we will look at it. So you can create user defined data types using the data types, and the data object is essentially a named entity that has the values, type, and signal kind, right? Because the signal kind, because you say you have to declare it as net or a variable, and then those can be like either integer or real, and then depending on that, the data values that it can take. So there are some of the definitions as the formalized terms that are provided in the SystemVerilog. Okay, so in the SystemVerilog, we have this new data type called logic. We have seen the usage of this particular logic data type in the FIFO test bench as well. In the interface, we had created everything of the type logic, if you remember. And this is defined to describe like a generic 4-state data type, and it's exactly same as Verilog reg. Okay, and what the idea that SystemVerilog is trying to bring in is that it's trying to make things more explicit. Some certain things were more implicit in case of Verilog, and it wants to make it more explicit. So for example, a wire my wire, the way I could declare it in the Verilog, now I can declare it as wire logic my wire, and it makes it clear that okay, because it's a logic and the logic is a 4-state data type, I'm formally defining it as a 4-state data type, so this is going to take 4 states. It's making it more explicit. Along with that, this the logic data type has a lot of value in SystemVerilog. You can actually use this for doing almost everything, unless and until you have like a multiple drivers, right? It doesn't support multiple drivers. Okay, but rest of it, like for example, you can use a logic data type as a LHS for your continuous assignment statement as well, and you can use the logic data type on port, and then you can actually use it for modeling all your input output ports. You can use it for like your point to point, like use it as a wire when you are connecting, use it as a variable which can be driven from always and tasks. You can use it as target for your continuous assignment statement. All your input and output ports can be modeled using logic. So except for the fact that unless and until you have multiple drivers, only when you have multiple drivers is when you really now need wires in SystemVerilog, not in Verilog, in only in SystemVerilog, okay? Because logic data type is not available in Verilog, it's available only in SystemVerilog. That you can use a logic data type for almost everything except for the multiple driver, which is not a very frequent occurring case in everyday life. So we can use logic data type for most of our connections and the driving part in the as far as the test benches are concerned. Okay, so we called out that we can use logic for most of the purposes, but like even for the point-to-point net type of a connection, we can use a logic data type, but the logic data type is a variable, it's not a net. Okay, that point we have to keep it in mind, and this small code snippet demonstrates the difference. So like let's say I have wire my signal 0 equal to A and B and logic my signal 1 equal to A and B, same expression exactly. So what happens in case of your wire is that line number 3, it becomes a continuous assignment statement. What that means is if in future the values of A and B changes, then the my signal 0 gets updated. Whereas when I declare it with a logic and we declaring this expression A and B, if there is a change in the value of A and B, that won't reflect in the my signal 1. So what happens at the time 0, it will evaluate whatever the based on the values of A and B, it will evaluate this expression, and the output of this expression A and B will be assigned to my signal 1, and thereon it remains constant, it won't change by itself. Whereas in case of wire declaration, it will keep on changing. So that is one concept that you need to keep it in mind. But if you want to build, let's say, the equivalent of this statement 3 using the logic, then you will have to create a continuous assignment statement by yourself, and then it will behave in the equivalent form. So what this means is, in summary, if you are building a Verilog test bench, I am talking about test bench. When I mean test bench, I am talking about test bench top. These rules I am not talking about when you drive internally within the DUT. I am not talking about DUT. I am talking about how you connect your DUT in the test bench. That is what I am talking about. Okay. So when you connect a DUT in the Verilog test bench so the connection between your test bench and DUT, for your DUT output ports, you have to use wire. So you have to use a wire data type for DUT output port to your test bench input connection. You have to use a wire, and for your DUT input ports to test bench connection, you have to use reg, because your test bench will drive using reg and it will read using wire. Whereas if you are building it with SystemVerilog test bench, then you can use logic for both the input and output ports, provided you do not have multiple drivers. As long as you do not have a case where you have multiple drivers, then you can use logic, and that will simplify your overall process of setting things up. Okay, so there are different net types that we had seen that available in the Verilog. They are available even within the SystemVerilog as well. And like a lot of modeling characteristics is provided. You can model the strengths, and you can even model the capacitive storage for a DRAM type of an interface. It relies on the capacitive storage, so even that can be modeled. And the idea of these nets, as we have talked about, they all have a built-in resolution function. So even you can create a user-defined net. User-defined net meaning that it can have multiple drivers, and then you can define your own user-defined resolution function. So each of these built-in net data types that we are talking about, the wire is the one that we have frequently been using. But if you see here, the logic doesn't come over here. It's only the wire that comes, because it's a net data type. So you have wired AND, wired OR, tri-state, tri-state AND, so supply 0, supply 1. So you have various built-in net types, and each of those net types will have their own behavior, and wherever these net types are supporting multiple drivers, they have their own resolution functions, and you can create your own net types with your own user defined resolution functions. We are not going to go into details of each one of them because they are very specialized and they are not used in most of the common verification projects. They are mostly used in your as far as I have seen, that they are used in your VLSI library developments. So we are not going to go very deep. This is something, the concept that you need to remember is that you have these different built-in data types. They support multiple drivers, and then they will have a resolution function, and depending on the resolution function the final value gets decided, and you can create user defined net types and you can define user defined resolution function, and as and when you need in the future you have to refer LRM to find out more about these. So as we talked about at the beginning, the SystemVerilog is trying to make things a little bit explicit, but some of these concepts, like for example this variable with the where keyword, it exists but it's not very frequently utilized. So variable in the context of SystemVerilog is just an abstraction for your data storage, and it stores the value when whatever is assigned, and then it retains it till the next assignment takes place. And in an assignment actually acts as a trigger for the variable to change the value, and where keyword is introduced to declare a signal kind of the type variable, and the syntax is generally you say where the keyword to indicate that it's a variable, not a net data type, and then you provide the actual data type and the name. So some example could be, I could say where and it's a byte type of a variable, and then I can say data byte, but it's equivalent to byte data byte as well. Whenever you say byte data byte, it is going to default to a variable, not to a net, right? So even if I create where n, it defaults to logic n, so default data type will become a logic. I can also say where logic n as well, so that also is equivalent. So I can say actually where reg r as well, so the register data type, but it is of the type variable, so that I'm making it explicit. So some of these is making it explicit, but it's not mandatory to use it. You can use optionally to make the intent more clear. So these are some of the integer data types taken from the LRM. So I have a shortint, which is a two-state data type and 16-bit. You have int, that is your two-state data type, and a 32-bit signed integer. So there's often a confusion between int and integer. So the difference between int and integer is something that you might want to pay attention. So the integer is a 4-state data type. It's also a 32-bit signed number, whereas int is 2-state data type and still a 32-bit signed number. You have longint, which is again a 2-state int basically, right? So that you can remember longint is again a 2-state, and a 64-bit signed number is what it supports. And then you have byte, which is again a 2-state data type with the 8-bit signed integer, or a ASCII character can also be represented. So your string, which we will see eventually, will become an array of bytes because it can hold the ASCII character. And then you have a bit data type, that is 2-state data type, and it can be like user defined vector size can be defined, and by default it behaves in a unsigned manner. Logic is again, as we have discussed, it's a 4-state data type. Then user defined vector sizes can be defined. Unsigned default behavior is unsigned. Reg is again equivalent or same as logic. It's again a 4-state data type. You can define user defined vector sizes. It behaves as unsigned. Integer, we already looked at it. Time is a 4-state data type, and it behaves in a 64-bit unsigned number. Then when you assign anything that is small to large, for example, if I assign like a shortint to a int, then the number gets 0 extended. Okay, and when you do the 4-state to 2-state conversion, then your x and z's are converted to 0, And the sign of numbers can be like, for example, we talked about there is a default sign. So the default sign can be controlled using this additional keyword. So if I want int, I know that by default it's assigned. So if I want an unsigned, then I will make it int unsigned va. And this is an important point, because what happens while you are declaring your constraints, if I declare a rand int, and if my constraints are not very clear, then it can go to like it can try to satisfy the constraint using the negative numbers as well. Like, unless and until I explicitly make sure that if I declared it as an int va, I have to explicitly make sure that if I do not want negative numbers, then I have to put va greater than 0 as a part of constraints. If I don't do that, if I forget to do that, then it can take negative numbers and try to satisfy your constraint. So that is where you need to be careful, that unless you really want to do something signed, you look at what is the default sign of a number, and if you don't want a signed number, you make it unsigned. So this is something that you want to keep it in mind. Okay, so there's a real data type, or what we call it as a floating point numbers, are also supported in the SystemVerilog. So you have this, when you declare a variable with a real keyword, the data type is same as C's double. And when you declare it with a short real, the data type, if you have been coming from a C background, it's equivalent to float. And the real time is another data type, it's same as real. Okay, so this is what you can use. We generally, while we are logging, if you want to capture something, if you want to measure something, then you should be using real time data type. And with the real data types, not all the operations are supported. There is a limitation that which operators are supported. When you start using real numbers, you can refer to LRM to get to know about it. And then the edge event control is not possible with a real data type, whereas with the int data types it's still possible. It will look at the lowest bit and figure out the edge control. That's not possible. Then you cannot do like a part select, because it's sort of a whole number as a whole, right? So so that's why you cannot use the part select with the real numbers. And then whenever you do an conversion from real to integer, it rounds it to the nearest integer value, real number, it rounds it to the nearest integer value. That is something that you want to take a note. Okay, so SystemVerilog also supports a string data type. So string is nothing but your ordered collection of characters, and then the length of strings can vary, so that I can declare a string variable with a certain initialization, and then during the execution I can change it to a different string. So the variable length it can accommodate, because there is a dynamic in nature, and it's actually made up of byte. So it's actually a byte array, and hence its characters can be accessed using index. Like, for example, I can say, s1 of 0, and then the appropriate letter out of that particular string can be extracted and can be utilized. And then strings are very useful in formatting your debug messages. So what you can do is you can declare a string variable, and you keep accumulating all the variable information into one string. And after the whole thing has been accumulated through series of processing that you have done through various functions, and then you can display the logging messages. So that is something that you can do. There are various operators are also supported on the string. We will look into it a little bit in more detail when we look into the operators. But just since we are talking about it, you can do the string concatenation. You can use this curly braces, and any comma separated string list of string variables, it will result in concatenation. You can do replication. So again, if I can put an integer number, and in the second pair of curly braces a string, if I put it, it will replicate them. You can do like various the logical operations on the string. The ASCII based comparison will take place to figure out the result of these operations. So that is the thing about the string data types. Okay, there are a bunch of methods also supported on the string data type. So you can find out the length, because the length of string can keep on changing depending on what you have assigned. You can do your data type dot length, which returns the number of characters in the string. You can replace or you can get a particular character at a particular position using the put C and get C functions, and then you can convert it from an uppercase to lowercase and lowercase to uppercase. Then you can extract a substring formed through two different index positions, so you can extract it, sometimes is useful. And then you have these type conversion functions, wherein, like for example, a to I returns an integer corresponding to ASCII decimal representation in string. So what happens is that like if I have a particular number represented in the form of a string, but if I want to use that number as a number, then the representation, the internal representation is different. So that is where, like for example, in a file I have entered a particular number, that will be a string, and if I read that file into a SystemVerilog, now it's still present in the form of a string, so I can't directly do a arithmetic operation. Like if I do a arithmetic operation, it will become an ASCII arithmetic operation, not a like a integer arithmetic operation. So what I need to do is, at that point I need to do like this a to I or the appropriate conversion function, depending on what the base that I'm using, right? Whether it's a decimal number system or hexa decimal number system, or octal, or a binary, depending on what number system I'm using, it will come in as that particular type of a string, and then from that string to that format, the actual format, I need to convert, and then only I can perform a corresponding arithmetic operation or the other operations on those. So these functions are useful. So sometimes why I'm bringing this up and showing it is, sometimes we do really store some of the stimulus information inside the file, and when you read it, so you might have to do these conversions before applying it to the actual DUT. And then there are reverse also, that you might want to reverse convert it, whatever you have, and store it into some output value for post processing for the conversion to string. So these are the functions that you can utilize. Okay, so there is a event data type as well. We will look at from the use case point of view for the event data type when we go to interprocess communication, because it's important. But in this context, we are just studying it as an data type to make the overall like the understanding of data types complete. So event is a data type that's used for the communication between two or more concurrently active processes. And like for example, on a clock, we say at pausage of clock, right? So we can create events on the event data type that we can explicitly trigger, and then we can capture those events and do some processing. So that is the use of the event data type. So one process can trigger it, another process can capture it and use it. And as a data type, you can assign one event data type to another, and then they will link together, so they will point to the same. So you trigger in one, like for example, here I have done and done2 equal to done, so done2 and done are now same. So if I trigger on done, I can either wait on done or done2, and they will represent the same. So it's a concept of aliasing that happens when you do the events. It's similar to the class handle assignment that we will see in the subsequent sessions. So they can be compared with another event variable to find out whether they are same. They can be assigned to null to kind of eliminate the synchronization that was established. So the SystemVerilog, whatever the data types that we are discussing, that can be extended using the user-defined types. Typically, whenever we talk about user-defined types, the enumeration type that comes into our mind, we will look at that specific one later. But even with the existing types, you can create, like for example, what we talked about, like many times we need a two-state integer data type that is unsigned. So if I'm going to need it every time, I can say typedef int unsigned as int p. Now I can use int p is a new user defined data type that I have created out of the standard data type that is present, and then I can say int p a comma b, and that's equivalent to say me saying int unsigned a comma b. So now everywhere I can use this data type, and this is the enum data type that I have created using the typedef. And you can sometime you can actually declare type without really giving the actual information about the type, and then you can provide that later. Like for example, many times when we come to class, we will see it that like A wants to extend from B class and B class wants to extend from A class. Now there is a circular dependency. So how do you resolve that? And unless A is defined, now I cannot define B, and unless B is defined, I cannot define A. So in those cases, I can just say typedef class and I give some name to it, and then the compiler knows that I'm going to provide the declaration for this particular identifier later, but allows me to use it. But if that doesn't get defined towards the end, then it will still result in error. For that moment, I can continue ahead by providing the typedef declaration, and so that way also it is useful to provide the declaration, and then the definition of it I can provide it later. So there's another usage for the typedef. So often what happens is we have few specific constants that are provided, here I have, for example, some base address of various IPs present in an SOC, right? Like a UART is present, UART0 is present in this particular base address, UART1 is present in this base address, so I2C1 is present in this base address, so on and so forth. So these constant values have some significance. So when you have such scenarios, instead of just using these direct values, which may not strike when we either read the code or when we are trying to debug something, we can give names to these constants using the enum data type. And if I don't use typedef over here, then what it forces me is that I have to declare the variables of this enum data type right over here. And then if I want to use this later, I can't do that. I have to come back to this particular place only and declare it between this end of the data type name. I have to give a space and provide the variable names. But if I do typedef, then I can use IP base address underscore t anywhere in my code, right? That is the benefit. Or I could have various states that I want to represent, and in case of RTL, it allows me that I can use different encoding for these states. I'm not binding to the encoding, but I'm giving a named values to these various constant values. And the default data type that this enumeration uses is int. And what you can do is you can actually, whenever you have an int value, although it is stored as an int value, like let's say I have stored this particular value in a variable of this type, I can actually display that value in the form of UART0 or UART1 instead of this the hexadecimal representation. So that helps me in doing the debug when we use the enumeration data type. So I think like even in the 5.4 Testbench for the transaction type, we had used the enumeration data type. So that's something that you can go back and refer for the real use cases. Okay, so we have talked about various data types now, and we know that when we can use those data types and declare different variables. Now when we do that, we have to understand this concept of scope and lifetime. So what this means is, scope means that once I have declared a variable, who all can see it, that is the scope. Okay, and lifetime is how long that variable will be available for usage. So this is the concept of scope and lifetime. So now let's look at few cases. So if I have declared a variable which is outside a module, program, interface, checker, task, or a function, right? So I've declared it. So I've created a module, let us say, and then outside that module, right? If I have declared that particular variable, then the lifetime of that variable will be static. That is, it will be available throughout the simulation, and it means local to the compilation unit. Means whatever the like if I can have like a multiple modules or multiple program blocks within that file, whatever that file will be my compilation unit. So whatever I have declared below that will be able to see the variable. So that is what is the scope over here. And then if I have a variable which is declared inside the module, program, interface, checker, but outside the task, process, or function, right? So as soon as I've entered the module, if I declare the values, then the lifetime of those variable will also be static, that they will be available throughout the simulation. But that value cannot be seen, like if I have now in a single file, if I have two modules, if I have a variable within the module, then that variable will not be visible to another module. Although that module is present within the same file, it still cannot see it. Okay. And so if they have declared variables inside a static task, like in Verilog, by default for module, it will be static, right? So if I have declared it within a static task or a function or a block meaning begin and end, then the lifetime of that particular variable will be static and the scope will be local. That will be visible within that task or within that particular function and not the outside. And although I might have a static task function or a block, but I can create variable saying like automatic, right? Like I can say automatic int something. So now what happens is the lifetime is the lifetime of call. Lifetime of call means as long as that particular function is called and it is active, only during that time the variable will be available, and that particular variable will be initialized on every entry. So every data type has a default value, like for example class data type will have a null default value, so that gets initialized on every entry. So on every entry it gets initialized with its default value that is defined by the LRM, and it will be local to that particular task or function. Now like for example in the class all the tasks and functions are automatic by default. So if the variable is declared, or you can create within an module automatic task or function as well, both the ways. If you declare a variable in an automatic task or function or a block, then again it will be during the lifetime of a call, and it is initialized on every entry, and it will remain, the scope will remain local to that particular task, function or a block. So the key idea that you need to understand is that there exists this concept of scope and lifetime, and then depending on the situation you need to look at it and understand. I think most of them are like very commonsensical, but this concept is what you need to really remember, and the individual scenarios and cases always you can refer to LRM and resolve, as long as you know that this concept exists. Few more cases of the scope and lifetime. So in an automatic task function or a block, I can have a static variable. Okay, so if we do that, then the lifetime of that variable becomes static. That is, it gets allocated in the memory, and it will remain allocated, and it will retain the value, but the scope will still remain local. That is, only when the task or function is executing, those will be able to access this static variable, but it won't be visible outside. And actually the fork and join, they also have a variable declaration area. We will discuss about those when we talk about the process in the procedural programming. But for now, just understand that I can declare a variable within the variable declaration area of fork join, and the lifetime of those will be like till the fork join block is active, and all the process spawned by those blocks will be able to see the variable that I have declared within the fork join declaration block. Let's look at one of these examples of how the automatic versus the static lifetime differences show up, right? This is just a theory, but how does it affect when we look at it in the real life usage? So here what I have is I have two for loops, right, and two nested for loops, and in one of the nested for loops I have it as a automatic, and in another one we have it as a static. Okay, so we are looping the first outside loop for 3 times, and again inside loop also we are looping for 3 times, and we are initializing the variable after we enter the first begin and end, and in the next begin and end we are incrementing it and we are printing it. So when it is automatic, what happens is every time the execution enters this block, it gets allocated and gets initialized. Okay, so here I'm allocating and I'm initializing, and then when we execute the inner loop, it increments, but after incrementing, when it comes out of inner loop and goes back to the outer loop, it is getting reinitialized, and that I can see in the values printed. So it prints 1 2 3 when it executes for the value 0, and then again it gets reinitialized and prints 1 2 3 for the value of index I equal to 1, and then again 1 2 3. So it's getting reinitialized. Whereas when I make it as a static, it gets allocated only once, and it won't get reallocated and reinitialized when I reach back to the outer loop, and hence if I see the values that are printed, it continues. So this is the way the lifetime manifests when we do the real usage. So we have seen various data types, right? And then when we do that, question in our mind will come, if I have a variable of type 2 and if I assign it to a variable of type 1, or if I have a variable of type 2 and type 3 and I perform some operation and assign it to a variable of the type 1, what happens? Right? Like if I take a two integer numbers and assign it to a short integer, or if I take a real number, perform some addition and assign it to integer number, so on and so forth. So I can have a different data types that I could be just directly assigning, or I might be performing some operation and assigning the result to a different data types. What happens? How does the simulator behave? This is called type compatibility, right? It is dependent on how the rules of type compatibility are defined, is what decides how it will behave and what will happen and what is allowed. So that is what the type compatibility provides. And whenever we do like usage in the some of the constructs, or when we do the operation, it requires some level of type compatibility in order to work. And there are five different type compatibility that have been defined. And what you need to understand is two things. One is that this type of an concept exists. That is the first thing that you need to be aware, that there is a concept of type compatibility for the operations to be performed. And the way you generally discover is you may not be able to remember everything, but then certain compile failure will happen, or certain runtime results will become not something that you really expect. And then at that point you need to remember that, oh, I have to look at it, and probably there is some type compatibility that might have gone wrong. And that is when you go back and refer to these and make sure that you find out a solution. So there are a lot of rules. We are going to look at few of them to for you to become aware. And anytime when you encounter issues, so on at that point you go back and refer to more and more rules and try to understand what has gone wrong. That is the general way you use it. You cannot remember all of them on the top of your head, okay? But the five rules are: there is a matching type, then there's a equivalent type, there's a assignment compatible type, cast compatible, and non-equivalent. Now we will understand what each of these mean. Okay, so the way this works is, some operation or some construct might say, okay, this operation can be performed on matching types. So now you need to know what is the definition of matching type. So all built-in data types match with every occurrence of itself. What does that mean is that if I have declared int unsigned a1, and then after some other declarations, if I have int unsigned a2, then it's the occurrence a1 and a2 are like, the data type occurrences of itself. So those are matching types. I know some of it might seem obvious and some of it is non-obvious, but those are the rules. So like here, if I see typedef bit node, then like the data type, any of the, if I have declared, let's say, node, and I have declared n1 n2, and bit I have declared b1 b2, then b1 and b2 are matching types with n1 and n2. So that is what it means. That seems again somewhat obvious, but look at this one. So this one will be strange. So I have a struct packed, and I know we have not studied it yet, but for now take this on a face value. So we can create a struct packed structure. Int a and int b are the two members. I have declared ab1 ab2 immediately. So there's no type def. Like this is the point that I was trying to make in the one of the slides. So there's no type def. So now you have to declare variables over here, and this ab1 and ab2 are now matching types. Very obvious. But if I now create one more struct int and b is exactly same. If I declare ab3, then ab3 is not the same type as ab1 and ab2. Okay, so that is the rule. Okay, then if here I have typedef bit signed 0 to 7, some whatever type etyb, this does not match with the byte type, because byte is bit signed 7 down to 0. So the order is different in the range. So they are not the matching type. So this is the definition of matching types. So in the previous slide, we saw it for a single variable, how the matching type is declared. Now, if we have the arrays, then how does it work? Let's understand it. So for the arrays, two array types to be called as matching types, then we need to have both of them to be either a packed or unpacked. I think we will look into more as to what is packed and unpacked when we go to the aggregated data type session. But for now, just take this on a face value, and they have to be same kind of array, that it has to be a fixed size or a dynamic or associative or a queue. So both of that has to match, and then if it is an associative array type, the index type has to be matching, and then we have to have the matching element types as well. And then fixed arrays, like we create like a 7:0 or 0:7, same left and right range bounds should be present. Okay, so one example that we can take over here, if I could define a array of 256 bytes, and I can define it with like bit signed 7:0, right? This is equivalent to byte, so I can have again declared it mem bytes. So in this case, both the types are of the type matching, whereas if I create for example, two nibbles, right, which is two of them and 4 bits each, so totally 8 bits. And if I declare a my byte, which is of total 8, because the range indexes and the dimensions are not matching, so byte and the nibble over here, they are not of the matching types. Again, as we discussed, I think some of them are obvious and some of them I think you will discover as you do it, but you need to keep the concept in mind. Okay, the matching type is slightly stricter than the equivalent types. So let's understand how. So if the two types match, obviously they are also equivalent, because as we talked about, matching type is more stricter than equivalent. So if they're matching, it is equivalent. Then so that is where, if you see, like if we have a enum or unpacked struct or a unpacked union type, is equivalent among the objects declared within the same declaration, right? So I have created this struct ab1 ab2. ab1 ab2 are matching and they are also equivalent types. Okay, so ab3 for example is not equivalent to ab1 and ab2 for the unpacked, and for the packed arrays it is slightly different. If a packed arrays or a packed structures or packed unions and built-in integral types, they are considered as equivalent if they contain same number of total bits. For example, we had seen in the previous case, like two nibbles didn't form, like they were not equivalent to 1 byte, although the total number of bits were same. But here in this case, if we look at it, we have a 1 byte and we have created one pack struct which contains two nibbles. Okay, and we are calling it as an unsigned integer of 8 bits. They are both equivalent because the total number of bits are same. Now this equivalence forms the change for the equivalence of arrays. So for a dynamic array, associative array or a queue type, they are considered as equivalent if they are same kind of array, which was the requirement for even for the matching type, and have a equivalent index type for associative array, which was same for the matching type as well. But this is different, so they have equivalent element types. This is not a matching type, but it's the equivalent element type. So if the array is made up of equivalent element types, although they are not matching, but still the arrays are considered as equivalent. So that is how the definition of equivalent types is defined. So any equivalent types or non-equivalent types that have implicit casting rules defined, then they are called as assignment compatible types. That's a definition. Now what that means is, like for example, all integral types are assignment compatible. That is, if I assign longint to int or int to a shortint, then there are rules. Okay, when you do the assignment from a bigger data type to a smaller data type, there could be a loss of data, but there is an implicit conversion rules, or which are also called as like a casting rule that is defined. And there could be a possibility that this such a compatibility could be in one direction. For example, now as we know that enum is of an integral data type, that is, if I don't provide a data type while declaring enum, then it is of the integer type. So now I can assign an enum to int, right? That is possible. But if I assign an int to a enum data type, then you need an explicit casting rule. So there is, from enum to int, there is one way compatibility. So what this means is that if the language has a built-in rule for assigning one type to another type, and then those are assignment compatible types. And whenever you do incompatible assignments, either some of them can detect it during the compile time itself, or some of them depending on the data type could get detected during the runtime, right? So that will definitely result in some form of an error. And when the casting rules are not present, implicit casting rules are not present. So casting rules can also be defined explicitly, and those explicit definition of casting rule can be either a static or dynamic. So let's look into them. Okay, let's understand what are cast compatible. So all assignment compatible types plus non-equivalent types that have defined explicit casting rules are cast compatible. So here we are doing a explicit casting. Okay, and there are two types of casting operators for explicit casting. It's a static casting and dynamic casting. So this concept is important. So what is static casting is that we have implicit casting rules, and when we call out the implicit casting rule explicitly, and it's called as static casting, and it is static casting also because it happens at the compile time. So it provides somewhat better performance because it is happening at the compile time and there's no runtime penalty. And then there is another type of casting called dynamic casting, where what happens is the two types that we are trying to assign among each other, they are not ordinarily sort of valid type of assignment, but although the data types are different, they could be under the hood have similar capabilities. So this is something that we will see very frequently happening when we do the inheritance, when we do the polymorphism concepts, when we do the object orientation. So this dynamic casting will be more prevalent in that context, or at least they have, like, in the context of usage, we have the similar capabilities. So as a user, you are taking the responsibility of assignment. So that is how you are doing it through the dynamic casting, because you understand that it will work fine in that particular context. And dynamic casting actually happens at the runtime. So, and then you'll have to check whether the casting succeeded. There are rules for governing what is compatible in the dynamic casting. So, and it has to be checked whether the casting was successful at the runtime. So in summary, you can do static casting or you can do dynamic casting. Static casting is nothing but invoking the implicit casting rules, and this takes place at compile time. And dynamic casting is between two different types altogether that don't seem compatible. They are very different data types, but you try to do the assignment using the dynamic casting, and this happens at the runtime, and it needs to be checked that whether it took place correctly or not. Okay, so static casting, as we have looked at it, takes place at compile time, and the data type can be changed by using the this cast operation. And the way you do the cast operation is that you put the expression in parenthesis and use this apostrophe. That's your casting operator. And static casting, one thing you have to be careful is it does not provide any error checking, and it's high performance because the check for cast compatibility does not need to be done at runtime. So you don't keep on checking it, once happens at the compile time. So for example, if I write a pseudo casting expression like this, a, and I'm casting it to the type 1, for this expression 1 I'm casting it to type 1, this expression 2 I'm casting it for the type 2, and I'm adding both of them together and storing it in this value a, is equivalent to me declaring these two temporary variables of temp1 and temp2 of type t1, like a cast t1 and cast t2, and then I am saying temp1 equal to expression 1. Now as these two types are different, there is an implicit casting rule that is getting invoked here, and there is an implicit casting rule that is getting invoked here. Now this implicit casting rule, I am here invoking it explicitly. That is what is happening. And then it's equivalent to a equal to temp1 plus temp2. Now the question might come, why is it not doing automatically? Because the compiler won't be able to detect this. So we have to do this casting explicitly. Let's look at some more examples that will clarify why it needs to be done explicitly. So here are a few examples of static casting. So here what's happening is I'm multiplying two real constants and I know that the result is going to be real, but in this case I am sure that the result will still be valid in the form of an integer, or maybe I don't care if there are decimal results. So I can cache this to int, and if there is any overflow it will get truncated, and that truncation won't flag any errors. That is my responsibility because I know that the results can be casted. So I'm explicitly casting this result of multiplication to integer, right? I'm explicitly forcing it. And here let's say I am doing the concatenation of two 8-bit numbers, and I don't want this concatenation to be like, let's say if I'm assigning it to even 32-bit integer, I still want it to be of the type shortint, then I can cast it to a shortint and force it to 16-bit results, right? Instead of it becoming a general 32-bit int. And here let's say I have a logic signed 8-bit number, so when I'm assigning a 4-bit number, it might not treat it as a signed number, so I am explicitly forcing it to be signed, and hence the overall value stored in the registers become -4. Or this is the, like I have an enum, and enum we know that by default has a integer data type values assigned. So the S0 will be assigned with value 0, 1, 2 and 3. So those will be the integer values. So now let's say if I want to do like a current state plus 1 and I want to convert that to back to the enum, so I can just say state underscore t, and I'm doing a static casting, and it will add the value to the integer, but the result it will convert it back to the enum and store it back in the next state. So so as and when you know that the results will be compatible, but like for example here when I say next state equal to current state plus 1, it will convert it to integer, but it won't explicitly force the next state conversion to be of the enum type. So that I am doing it through the static casting. So this is where these are some of the use cases where you will find the static casting more useful. When you don't do it, sometimes you will see surprising results, or in some of the cases it will even flag the type incompatible type error. So at that point you can check it up and then figure out that this needs a static casting. Okay, so we saw the static casting and the static casting operator through that apostrophe. Now the dynamic casting is done through this system task called $cast, and the $cast allows you to do the dynamic casting as well as error checking. Both of them you can do it using this particular system task, and it can be used as a function or it can be used as a task. So it can be used in both the ways, and depending on the usage context the compiler will figure out how are you using it as. But when you use it as a function, what it does is the $cast attempts to assign the source expression to your destination variable, and if the cast becomes successful it will return the value 1, indicating that it is a success. So you can check it, like if $cast of whatever your source destination variable comma source variable, you can check whether that has happened, and if the cast fails then function doesn't make any assignment and returns 0. So that's how the $cast behaves. And when you use it in the task context, that is you are not doing the check, like you are not doing if, you are just directly just calling the $cast, that attempts to do the assignment of source expression to the destination variable, and if the assignment is invalid, that is if they are totally type incompatible, then runtime error will take place, and then but the destination variable will be left unchanged. So that's how the dynamic casting is done. Now we will get a question as to when to use static versus when to use dynamic. Like for example, the class data type casting that we are going to see eventually when we do the object-oriented programming is all dynamic casting, because anyway the word of class itself is dynamic. So any class handle assignments that we are going to do between different data types is going to be through the dynamic casting, because even when we do inheritance, the data type will become different. So the assignment between them will have to go through the casting. And the second one is, now, like for example, if we took this previous case where we were doing like next state equal to current state plus 1, now we don't know if the value that it is going to result in, is it going to be a legal value that can be mapped back here. For example, only the integer values 0, 1, 2 and 3 are legal. If I assign any other value to this data type, then it is not legal. Okay, so but I don't know whether that is happening or not if I do the static casting. So here I can do a dynamic casting. If I don't know whether the static casting can result in error, if I'm not sure about it, then I can do dynamic casting. So if I had a constant values during the compile time and they were none, or if I'm very sure that this value is never going to exceed, then I can probably use the static casting. But if I am not sure and that a value that I'm casting is all getting generated dynamically, then you can use a dynamic cast. For example, here I could say $cast next state with 4 plus 1, and then 5 is an invalid cast because that value is not present. So it's going to return 0, and hence we will see $error in cast type of a message. But the dynamic casting, now since this code has to execute every time whenever you are doing the assignment, it gives some performance penalty if it is happening very frequently. So this concludes the session on SystemVerilog data types, and we could see like how the different terminologies have been introduced and how the new logic data type, and then we could see some two-state data types, and then we were able to see like a string data type, event data type. So we have seen some of the new data types that are introduced within the context of SystemVerilog, and as well as we understood the concept of scope, that is how far a particular variable is accessible, and then lifetime, like whether it is a static or automatic, and we could see those concepts. And then we understood the concept of like the type compatibilities, the 5 different type of type compatibilities. We briefly looked at it. That's a very elaborate topic. We have only touched based upon some key details. And then we looked at the type compatibility concept. We looked at in the context of casting, and we understood that there are 2 types of casting. There's a static casting and dynamic casting. And static casting is essentially invoking your implicit casting rules explicitly and happens at the compile time, whereas dynamic casting is something that you check it during the runtime. And dynamic casting is much more useful in the object orientation programming, so which we will see more details about it when we look at the class in more details. So thank you for listening.